Welcome. We're moving beyond the simple one-click filters that have dominated social media for years. Today, we're taking a deep dive into the sophisticated AI-driven tools that are fundamentally changing the landscape of digital imaging. This is for those of you who aren't just users, but are builders, researchers, and engineers. We'll explore the underlying models, from generative adversarial networks to the now dominant diffusion models that power these incredible capabilities. Our goal is to understand how they work, not just what they do. We'll dissect techniques that offer precise control, enable unprecedented creativity, and are rapidly becoming essential components in the modern data scientists and ML engineers toolkit. So, let's look under the hood at the architectures and algorithms that are redefining the boundaries of visual content creation and manipulation. Let's begin with a foundational concept: generative fill and inpainting. This is far more complex than the content-aware fill you might find in legacy software. Instead of just sampling and cloning nearby textures, modern inpainting models possess a semantic understanding of the image. Early successful approaches used GANs, but the state-of-the-art is now driven by diffusion models, like those used in Stable Diffusion or Google's Imagine. When you mask an area for removal, the model doesn't just see pixels. It encodes the surrounding image into a compressed latent representation. It understands concepts like sky, brick texture, or reflective surface. It then runs a reverse diffusion process within that masked region, conditioned on the latent representation of the context. It essentially hallucinates a plausible patch that is coherent with the rest of the image's lighting, perspective, and meaning. The primary technical challenge, and where models still sometimes fail, is maintaining global consistency. A perfectly generated patch can still look wrong if it doesn't match the subtle, scene-wide lighting or grain. The next evolutionary step is moving from removal to guided modification. We started this journey with neural style transfer, famously demonstrated by Davies et al. This used the feature extraction capabilities of convolutional neural networks to separate an image's content from its style, allowing us to repaint one image in the style of another. But today, diffusion models allow for much more granular, intuitive control through natural language. Enter models like Instruct Pix-to-Pix. The innovation here was creating a massive dataset of triplets: an input image, an editing instruction like turn the cat into a tiger, and the corresponding output image. The model isn't just a text-to-image generator, it's fine-tuned specifically for the task of editing. Architecturally, it conditions the diffusion denoising process on two things simultaneously: the clip text embedding of the instruction and an encoding of the original input image. This dual conditioning allows it to make localized, context-aware changes that respect the original image's composition, rather than regenerating it from scratch. This is a paradigm shift from applying a global style to performing a specific instructed edit. For ML engineers, the holy grail is often specialization. How do we teach a massive, generalized model about a new, specific concept? This is where Dreambooth comes in. The technique allows you to fine-tune a full text-to-image model, like Stable Diffusion, using just a handful of images of a specific subject, say your pet. You teach it to associate a rare, unique text token, like a scus dog, with this new concept. The drawback is that this process fine-tunes the entire model, resulting in a large, multi-gigabyte file for every single new concept. This is computationally expensive and difficult to scale. This is where LoRA, or low-rank adaptation, provides a brilliant solution. Instead of retraining all the model weights, LoRA freezes the massive pre-trained model and injects very small, trainable pairs of rank decomposition matrices into the transformer layers, specifically the cross-attention layers. All training happens only on these tiny new matrices. The result is a fine-tuned patch file that is often less than 20 megabytes, a 100-fold reduction in FIs. This makes it feasible to train, store, and swap thousands of different concepts on the fly, a game changer for production systems. So, we've journeyed from intelligent content removal to instruction-based editing, and finally to efficient model personalization with Dreambooth and LoRA. The trajectory is clear. We're moving towards ever-increasing levels of control and specificity. The next frontier is about composing complex scenes and exerting granular control over the output. Technologies like ControlNet are leading this charge. By conditioning the diffusion process on additional inputs like depth maps, human-posed celatons, or canny edge detection, developers can now precisely dictate the composition and structure of a generated image. This bridges the gap between the unpredictability of a text prompt and the explicit control of traditional CGI. Looking ahead, these principles are being extended to generate coherent video sequences and 3D assets. What this means for us as practitioners is that these AI tools are becoming less like black boxes and more like programmable visual synthesizers, fundamental instruments for anyone building, designing, or working with intelligent systems.